In this unit, we have introduced kind of the idea of charge and how charges interact with each other, both conceptually and mathematically, in the last video when we talked about electric forces. So what we're going to talk about today is go a little more in depth with those electric forces when we talk about electric fields. So an electric charge, we'll call it Q, can exert its force on any other charged object, even though they never come in contact with each other. We already knew that from the last one. So every charge has this area around it where if anything enters that area, it can exert a force on it, and we call that area the electric field. And we can still say that this is kind of analogous to the way that gravity works, because if you climb up in a tree, you're not touching the earth, but it can still exert a force on you, and if you should fall out of the tree, it will bring you back down to the ground. So just because you are around the earth, it's able to exert some kind of force on you. That's the same way that an electric field works. Electric fields, kind of like gravitational fields. So we can represent electric fields graphically by drawing those force vectors that kind of surround a charge. So let's take a positive point charge. So we'll say that that guy is positive. Then to draw the field around it, we're going to take what's called a test charge. Anytime you do anything with electrostatics, electricity, you might hear the word test charge. All that means is just some really small positive charge. So in comparison to this one that we drew right here, ours is going to be a lot smaller, but still also positive. So if I put a positive charge right here, right next to this big positive charge, it's going to want to get pushed away. And of course my arrows are still going the wrong way. It will want to get pushed away. There we go. And the closer that it gets, the stronger that repulsive force is going to be. So if I put it, let's say maybe way out here, it's still going to want to get pushed away, just not quite as much. And if I put one in the middle of those, still getting pushed away. Not quite as big as the first, but not quite as small as the second either. What about on the other side? Which way would those arrows point? Well, if I put one really close, it's going to get pushed away with a really strong force. And that'll be the same no matter where we put it. It'll always go straight away. So if I put one down at the bottom here, really strong repulsive force. If I put one up at the top, still a really strong repulsive. So here's a little bit better picture of what that would look like. We have our charge Q, and though you can't see it, if we dropped our test charge at any one of these vectors, the vector shows us what kind of force it would experience. Remember, a test charge is always going to be positive. We can talk about we can talk about electric fields mathematically too. The electric field is a vector field, so you can see all these different vectors. At every point in space, we have some kind of vector that tells us what that electric field is going to do to whatever charge we want to test it with. So if we want to figure out the force F that's experienced by some particle Q, some charged particle Q, that we put into an electric field E, and keep in mind this electric field is created by some other charge. So Q is not creating the electric field. Q is experiencing the electric field from some other charge. So if we want to calculate that force, we have F. I'm going to say FQ because it's the force acting on Q. That's going to be equal to Q times capital E. So the charge of this particle we're dropping in multiplied by the electric field value for whatever other charge it's creating. We can take this equation that we just set up for electric fields and plug it into Coulomb's law because it's an electric force that we're talking about. That's the same electric force that Coulomb's law is talking about. So we could figure out the magnitude, or how big is the electric field created by some charge Q at any point in space. So all we're going to do is take Coulomb's law, plug it in here for FQ. Remember Coulomb's law here. And so we have that this electric force is equal to Coulomb's law, and it's also equal to this other one that we just set up for electric field. So we have two charges in Coulomb's law. We also have two charges in this electric field equation. One's just kind of hidden. So this Q would be either Q1 or Q2. And the electric field is due to whichever charge we didn't say before. So let's just call this Q2. We'll say that we're plugging Q2 into the electric field that was created by Q1. So if these two things are equal to each other, well, they both have Q2 in the numerator, so we could cancel that out to get E equals K Q1 over R squared. So what this says is the electric field generated by the first charge is equal to Coulomb's constant times the size of the charge divided by whatever distance squared. So however far away you are from the charge, this is how big the electric field will be at that point. There are times when you could be asked to calculate the electric field. There are also times you could be asked to draw the electric field due to a certain arrangement of charges. The AP test could very well ask you that for those graphical representations. So we saw above what would happen for just one charge. If you have one positive charge, all your vectors point straight away from it. If you had a negative charge, since our test charge is positive, all of the vectors would point directly into the negative charge. So let's look now at a couple more complicated cases. So when we have multiple charges, we're going to do the same thing we would do with a force. We have that idea of superposition. Two things being in the same spot at one time. So we'd have some electric field from the first charge, some electric field from the second charge. We just add those up. Keep in mind, when you add vectors, direction is a big factor. So if we have, let's do this example first, two charges where one is positive and one is negative. So one positive charge and one negative charge. Let's change the color to make that a little more apparent. So the positive one we'll say is red, the negative one will be blue. So if I put a test charge here right in the middle, the positive will push away, the negative will pull it closer. So my point will want to go directly to that negative. If I put one here, the positive tries to push it away along this straight line, but the negative one tries to pull it in, so it gets a little bit bent. One day I will learn how to draw these arrows. If I put one here, the positive tries to push away, the negative tries to pull it in. So the upward from the positive and the downward from the negative cancel each other out. All we're left with are the horizontal components. So what the positive charge pushes to the right with and what the negative charge pulls to the right with. And again, if I wanted to put one here, I'd get an electric field vector like this, and it works the same way on the bottom, actually the whole way around. Here we have a little more sophisticated drawing of that. So the positive pushes away, negative pulls in. We create this kind of bendy, circly shape connecting the positive and negative charges. What would happen then if we had, say, two positives? So one positive charge here and one positive charge here. Well, if I dropped one right into the center, then the charge on the left would push to the right. The charge on the right would push to the left with the same amount of force, so that charge really wouldn't go anywhere. So at the very center, when you have similar charges, there is zero force, so zero electric field. If I dropped one here, it would push away from that positive, and the same thing would happen over on this side. When you start to get into the center, this one would want to push straight away up and to the left, but this one's going to push up and to the right. So what happens is it kind of makes this bendy shape. So they bend and bend and bend. What you get right in the center is kind of an asymptote. So there's some spot in the center where it just goes straight up. It doesn't move to either side. Here's that same situation again, a little more sophisticatedly than my awful trackpad Adobe pencil drawings. We have our two positive charges, and you can see a little more clearly that area where they start to bend almost perfectly vertical. This situation would look the same for two negative charges. It's just that these arrows, instead of pointing away, would point toward. So for two negative charges, you get the same shape. If you have two similar charges, you get this shape. The only thing left to talk about in electric fields are some extreme cases where you have a line of charges, so an infinite line of the same size and sign charges and plane charges. So let's look at the case of a line charge first. So this blue line represents an infinite amount of all of the same kind of charge. Let's call them positive. So if I took a test charge and dropped it right here, so I have a positive test charge. My pencil is stuck on green. Alright, dropping a positive test charge right here. It's going to get repelled by the ones that are directly underneath it. It's also going to get repelled by all these others, and keep in mind they like to point away in a straight line. So this one points that way, that one would point that way. Any horizontal contributions are always going to be canceled out by something on the other side because of this symmetry across the straight line. So all we end up with, oh no, that was a pencil. I wanted an arrow. All we end up with is the superposition of the vertical parts. So because this line is infinite, it doesn't matter at what point we are. anywhere at this certain distance, the electric field is always the same size and of course always in the same direction. If we get a little bit further away though, the strength of the field starts to decrease. So we can see they get a little bit smaller. And then if you got even further away, they would be smaller yet. The only thing that starts to change when you have a line of charge is that the electric field strength is no longer related to the inverse of the distance squared. But you can see in this equation here, now it's just proportional to 1 over the distance. So anywhere along this line has the same electric field magnitude, anywhere along this line. So any line parallel to your line of charge will have some certain value of electric field. If we took that line and stretched it out into another dimension, so we would get a two-dimensional plane of charge, then we decrease that distance dependency. So you can see in the equation for the electric field due to a plane of charge, distance doesn't even matter. And in the picture you can see, no matter where we are with respect to this plane of charge, whether we're above it, whether we're really far above it, below it, or really far below it, the electric field is always the same size. And that's because you have kind of this infinite contribution to the vertical parts. So we still have that same kind of thing where the horizontal parts would cancel out. So whatever pushes left, there's something pushing right. Whatever pushes, I guess, into your screen, there's also something pushing out of your screen. These kind of three-dimensional ideas will get a little more important when we get to magnetism. We'll be talking about into the page and out of the page a lot more. But anyway, equation for plane of charge. The electric field due to a plane of charge is just E equals K times Q.